Hey guys, what's up? Today we're looking at tensor operations, or the algebra of tensors. So algebra of tensors. We can add tensors, multiply them by scalars, things like that. So algebra of tensors. So pretty much the whole time we're going to assume S and T are tensors. So assume capital S and capital T. I just write them in like block letters. Are tensors. I'm not going to write the components unless I'm like talking about explicitly adding component by component. So suppose S and T are tensors, then S plus T, which by component definition would be Sij whatever, let's see, R S T whatever, plus Tij whatever, or St whatever, would be a tensor. So is also a tensor. Is also a tensor of the appropriate rank. Basically, if they have the same rank, so the same rank and flavor, I like to call it, are tensors of the same rank and flavor. Flavor meaning they have the same number of contravariant and covariant indices, i.e. it could be like a 2-2 tensor. Both of them would have to be a 2-2 tensor. Or like a 3-1 tensor. Both of the tensors would have to be a 3-1 tensor for you to add them and still be a tensor of 3-1. So you can basically add tensors together. You can also multiply by a scalar and add them together. So also we can do linear combinations. So linear combination of tensors of the same rank and flavor are still tensors, because we can just multiply by a constant. So basically we have like a T1, tensor 1, so tensor 1, tensor 2, all the way out to tensor gamma, we'll call it. So these are all tensors of the same order and rank, or same rank and flavor. Then lambda 1 T1 Ij whatever Rst whatever plus lambda 2 T2 Ij whatever Rst whatever plus dot 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 lambda n Tn Ij whatever Rst whatever. This subscript here, the 1, just denotes which tensor we're talking about. It's not a tensor subscript. It's just to distinguish between the tensors. So that is also a tensor of the same rank and flavor. All right, so now what else can we do with tensors? We can add them together, we can multiply them by a constant, and it's still a tensor. That's fine. Something else we can do is called the outer product of tensors. So the outer product of tensors. This is a new operation for tensors that we're not really super familiar with, actually. Example, I'll just phrase it in terms of an example. Suppose we have tensor components Sij, I up, j down, And let's see, we have another tensor tk down. So I have a mixed order 2 tensor and a covariant tensor or a covector. So suppose these are tensor components or are tensors as specified by their indices. Then what we can do is we can produce something, a new tensor called pi up jk down, which is si up j down tk down, and it is a 1-2 tensor. And I will show you that it is a tensor. So proof that it is a tensor. I'll look at p I prime j prime k prime. By definition, that would be si prime j prime tk prime. And since those are tensors, we know that I can write that as partial x I prime partial x p. Not to be confused with the capital P. This is just I'll change it to q. If I can erase, just change it to q. And then partial x partial r partial x j prime s q r, q up r down, times partial x t, we'll call it partial x k prime t. I could use s. Let me use s right there. ts down. And now that would be partial x I prime partial x q partial x r partial x j prime partial x s partial x k prime sq r t s. But now this is just p q r s. So it transforms just like a 1-2 tensor would transform. So which is how a 1-2 tensor transforms. So it is indeed a 1-2 tensor. So that's called the outer product. So let's look at an example of what it actually does, though. It gives you like a new direction for your indices, but what does it really do? It actually creates new multiplications of all the component functions in every possible way. So let's look at an example of how we could create an outer product from 2 tensors. So example, let's see, given ti up, sj up are 2 tensors. Then we'll call it pij up would be equal to t1s1, t1s2, t1s3, t2s1, t2s2, t2s3, t3s1, t3s2, t3s3. If t is t1, t2, t3, and s is t1, or sorry, s1, s2, s3. So you basically take every component of t and multiply it by every component of s to create this new tensor. And now it's a rank 2 tensor, which is represented with a matrix. So an outer products produce a higher rank tensor. So that's kind of the takeaway. Produces a tensor with more components or more directions or more indices. Notice we had vectors basically to start with, vector fields, and we ended up with a matrix field by taking all the possible multiplications of the tensor components. and that produced a two-dimensional matrix. All right, so that's the outer product. Let's look at the inner product. This is actually more similar to stuff we've seen before in calculus. So the inner product of two tensors, inner product of two tensors. It's similar, except now we reduce the degree or the rank of the tensor. So let's say we have, say we are given, I'll just make up random ranks, S, I, J, K, L, M, N, T, A, B, C, D, E, F. I guess it doesn't have to reduce the rank, but two of the indices on the tensors are going to be the same. We're going to make them the same letter. So then the inner product or I should say then an inner product of S and T could be, let's say something like U, I, A, K, B, C, L, D, M, N, F. And what I'm going to do is I'm going to take S, I, J, K, L, M, N and multiply by T, A, B, C, D, J, F. So I'm basically taking this index out of play. It's no longer a live index, which means it should not appear on both sides anymore. So I will increase the rank of the tensor, but I will also lose a live index. So it's not a complete outer product. I'm actually taking these this upper index in the middle of S and this lower index in the middle of T and basically eliminating it. So this is called an inner product of two tensors. So this is almost outer product, but with the loss of the J index on S and the E index on T. So sometimes, like this one, the rank of the product would be higher than the original two tensors themselves. But you could have an inner product. Another example, you could have an inner product of like Sij, Tj. If you had those two tensors, this would give you a new tensor. We call it Pi. So it actually reduces the rank of the tensor to a rank 1 tensor, a contravariant tensor of rank 1. So this is now a 1,0 tensor. Whereas before this example, this produced a 5,5 tensor. When we actually started off with a 3,3 tensors. So it depends on what the tensors are that you start out with and the inner product that you're doing. So let's show that this inner product can indeed produce a tensor of the appropriate degree. We're just going to do these in, examples. No, we're not going to do them in like general. So example, suppose we've got something like Sij and TKLM. So suppose these are tensors. Then we'll call it we'll call it UJKM equal to SIJTKIM is a 1,2 tensor. 1,2 tensor. So, proof. This is similar to the things we did in chapter 3, except now we have multiple tensors multiplied together. I think we actually did an example like this in chapter 3, so on that worksheet. So U, J, K, M is going to be, let's look at U, J prime, K prime, M prime. That's going to be S, we'll call it I prime, J prime, T, K prime, I prime, M prime. Doesn't matter what I call the dummy index, but I'll just call it I prime. Now I know S and T are tensors, so I can write out their transformation laws. So that's going to be xi, partial xi prime, partial x p, partial x j prime, partial x q, partial x r, partial x k prime, partial x s, partial x I prime, partial x w, partial x m prime. S, let's see, I'm going to have a PQ up on S, and then a capital T, and then RSW down. And now what can I do? I can actually create a Kronecker delta with the I primes here and here. This is actually just going to be delta SP. Right, that's just the multivariable chain rule going backwards. We get a delta SP from that. So we get delta SP partial xj prime, partial xq, partial xr, partial xk prime, partial xw, partial xm prime. And SPQTRSW would be U, let's see, well, no, let's leave it as SPQTRSW and wait till we use the delta to change. So it's going to say S equals P. So I'm going to change S and P to be the same thing. So now this is equal to partial xj prime, partial xq, partial xr, partial xk prime, partial xw, partial xm prime, and then SP, well actually, yeah, I'll leave it as P, SPQTRPW. And now that is equal to U, PQ, oh, P is dummy, so it's UQRW, which is how a 1-2 tensor should transform. So this is partial xj prime, partial xq, partial xr, partial xk prime, partial xw, partial xm prime, UQRW, which is the transformation law of a 1-2 tensor. So indeed, this inner product will produce a new tensor of a new rank. Note, the inner product of a vector and a covector is an invariant, or a scalar, a tensor of order 0. So one very special case is to note that TI SI down produces a scalar. An invariant, actually. So doing an inner product of a vector and a covector, vector meaning contravariant vector, a contravariant vector and a covariant vector. T is the contravariant because it has one index up. S is the covector, covariant vector, because it has one index down. Doing that inner product produces an invariant, a scalar. Super important. Okay, cool. And we've already shown that the Kronecker delta, one up, one down, is a mixed tensor. Let's just give one more proof, more or less. Example, Tij is the matrix inverse of T ij up from chapter 3. So inner product, we'll call it Tik Tkj, would produce the Kronecker delta I up j down, and which again shows that delta I up j down is a mixed tensor, a 1-1 tensor. And we basically just showed that because it's an inner product, you can actually write the Kronecker delta as an inner product. So cool. Now, one more thing that we can do with tensors. I mean, there's plenty of more stuff that we can do with tensors, but the last one I really want to focus on is something called contraction. Okay, if we repeat an index in the same tensor, one up and one down, then we produce a new tensor, and we call that a contraction. So contraction is a repeated index one up and one down in a single tensor. For example, let's say that we have T I up, J up, K L M down, or just K L down, is a 2-2 tensor. So is a 2-2 tensor. Then let's say T I up, J up, J down, L down is a 1-1 tensor. Created by contraction. And we'll show that that is indeed a 1-1 tensor. So proof. So if we look at T I prime, J prime, J prime, L prime, since it's a tensor, it transforms like partial x I prime, partial x p, partial x j prime, partial x q, partial x r, partial x j prime, partial x s, partial x L prime, T P Q up, R S down. And now these two in the middle produce Kronecker delta RQ. So RQ, Kronecker delta. And so this is going to be delta RQ, partial x I prime, partial x p, partial x s, partial x L prime, T P Q R S. And now R is supposed to set equal to Q. So here we say R is going to be Q. And then we get, this is going to be partial x I prime, partial x p, partial x s, partial x L prime, T P Q Q S, which is a 1-1 transformation. So which is the transformation of a 1-1 tensor. So that's how a 1-1 tensor is supposed to transform. Cool. So indeed it is a 1-1 tensor. How many possible contractions are there for this tensor though? Well, I could take any of the two upper and contract it with any of the two lower, so two options for each index on the upper. So how many possible contractions for the tensor Tij KL. This is more like a combinatorics problem. So I can go with K, or I can go with L. J can go with K, or it can go with L. So two options for each of the two upper indices. So 4 total possible contractions. All right. So that's good stuff. 4 possible ways to contract the indices. And last thing we want to mention today is tensor equations. Tensor equations is super important in science. So tensor equations. So basically, if an equation or tensor equation so if a tensor equation or identity is true in one coordinate system, then it is true in any coordinate system. Which is incredible, because that means, for example, if Tij is equal to 0, then Ti prime j prime equals 0 for any, that should say if, for any coordinate system xi prime separate from the original coordinate system. So if you can find a tensor is equal to 0 in one coordinate system, it will be 0 in every coordinate system. Furthermore, it doesn't matter which coordinate system you use at that point. The tensor equation is true. You can pick whatever coordinate system simplifies the problem the most. And that's what happens in science, electromagnetism, general relativity, all these fields that use tensor equations. If you have a tensor equation in one coordinate system, you can use your favorite coordinate system or whichever coordinate system reduces the problem to simplify the problem the most. Basically like a triple integral. You didn't have to do the triple integral in Cartesian coordinates. You could switch it over to spherical or cylindrical. Well, the same thing's true now if you have like a differential equation or whatever. It doesn't matter what coordinate system you use. If you're a tensor equation, then you can use any coordinate system and solve the differential equation if it's a tensor equation. Yes, derivatives can appear as tensors. Kind of. We'll have to explore that some more once we get through chapter 6. We'll start to see derivatives showing up as tensors. So how do you get a tensor from a derivative? We already saw that derivatives don't really produce tensors, so how do we kind of like fix that? And that's what we're going to do in chapter 6. So another result, basically, example, if a tensor is symmetric in one coordinate system, then it is symmetric in all coordinate systems. It is symmetric in all coordinate systems. And you could also say if a second order tensor, second order or rank tensor is invertible as a matrix in one coordinate system, then it is invertible in all coordinate systems, which is super important when we get to the metric tensor. We actually get a real tensor that has some definition that we can explore and work with. Right now, these things are kind of high level. We don't really have much to go off of except the gradient and tangent vectors being tensors. But next chapter, we will get a real tensor other than the gradient and the tangent vector. We get a new tensor called the metric tensor, and it will be invertible, which is important. And since it's always invertible, and you can invert it regardless of the coordinate system. So it's pretty nice. We're going to get another real tensor coming up. So stay tuned. Just a little tease for the next chapter. I'm sure that's how you feel. You're just like, oh man, I'm so excited now for the next chapter. Anyway, thanks for tuning in today. Hopefully you guys stay safe. Have a good rest of your afternoon. That's it for today. We'll work some problems next time. Actually, no, we won't. We have an exam next class. Next time we actually meet together for class, that's not an exam. We'll do some problems on a worksheet and kind of explore some more of these concepts, more like these examples that we did here. So I'll talk to you guys later.